In this video, we're going to show how to use calculus to sketch functions. In particular, we're going to look at cubic functions here. So we are going to use the first order derivative and the second order derivative to analyze the structure of each of the curves and hence sketch them. So in part 1, we're going to look for the stationary points and classify each of them as either local maximum or minimum. We're going to find the y-intercept. We're going to find the inflection point or inflection points. We are going to find intervals where the graph is concave up or down. We're going to find intervals where the graph is increasing or decreasing, and then we are going to make a sketch. We're going to make the point that in this analysis, after these two, at this point we can actually make the sketch. So once we have got the stationary points and we have classified them, then we can make the sketch with the use of the additional use of the y-intercept. So that's what we're going to demonstrate, and then after that, finding these the rest of these ones we can actually do from the sketch, but of course we can use the calculus as well. Okay, so let's get on with the first one. So in A, we have got y is equal to 10 minus 9x plus 6x squared minus x cubed. So the first thing we're going to do here is to find the first order derivative. It's going to be minus 9 plus 12x minus 3x squared. While we are here, let's find the second order derivative as well, because we are going to need this to work out issues to do with concavity. Alright, then in part 1, we are going to find the stationary points. So stationary points, we are going to abbreviate this as P. Now, the stationary points are obtained by taking the first order derivative, equating to 0 and solving. So we're going to have minus 9 plus 12x minus 3 squared equal to 0. Now, you're going to notice that 3 is common in all the terms here. So in fact, if we divide by negative 3, this is going to be x squared minus 4x plus 3 equal to 0. And then this is factorable. This is x minus 1 into x minus 3. So this is telling us that either x is 1 or x is 3. So from this we see that there are going to be two stationary points. It's going to be one when x is equal to 1. It's going to be another one when x equal to 3. So we analyze these ones one by one. So let's start with x equals to 1. The first thing we're going to have to find is the y-coordinate of the graph when x equals to 1. And so for this, we go back to the equation for y and we plug in x equals to 1. When we do that, that's just going to be the sum of the coefficients there. So we're going to have 10 minus 9 plus 6 minus 1. This works out to 6. So this is telling us that the stationary point is at 1, 6. So 1, 6 is a stationary point. Then we need to determine whether it's a relative maximum or relative minimum. We are going to do that by using the second order derivative. Second order derivative tells us about concavity. If it's positive, then the graph is concave up. If it's negative, the graph is concave down. So we're going to substitute x equals 1 there, 12. So this is going to be 12 minus 6 times 1. So this is going to be 6. This is positive. So this is telling us that the graph at 1, 6 is concave up. The graph at 1, 6 is concave up. This is telling us that 1, 6 is a local minimum. Because if the graph is like this is the lowest point in that neighborhood. All right, so that sorts out the analysis of the stationary point at x equals to 1. Then next we go to the stationary point at x equals to 3 and perform a similar analysis. So the first thing, we need to find the value of y. So if we plug into the y equation, it's going to be 3 squared here and 3 cubed there. So this works out to 10, which means that 310 is a stationary point. Is it a local maximum or local minimum? Now, in general, if you have got two stationary points, it is impossible for those two to be of the same nature. So you can't have like two minima next to each other, or you can't have two maxima next to each other. If there's a minimum, then there must be a maximum before you get to another minimum. All right, so we expect this one, since this was a minimum, we expect this one should be a maximum because there's only two. But let's let the maths do the talking. So if you plug in 3 into the second order derivative, this is now going to be 12 minus 6 times 3. This is negative 6. This is less than 0, which tells us that at this point the graph is concave down because the second order derivative is negative. So this tells us that 310 is we can use local or relative there. So 310 is going to be a local maximum. Okay, then if we find the y-intercept, then after that we should be in a position to make a sketch of the graph. The y-intercept is just going to be given by the constant in the y equation. So 0, 10 is the y-intercept. All right, so now we have got 3 points on this graph, and these 3 points is the 3 points, but also the nature of the two stationary points. So we have got a local minimum, which means a point where the graph is shaped like that at 1, 6. We have got a local maximum where the graph is shaped like this. This is at 310. And then we know the graph also goes through 0, 10. So from this we can make a sketch of the graph. And this is how it's going to look like. So the first thing we're going to do is just make a little survey of our points of interest. 310 is in the first quadrant. 1, 6 is also in the first quadrant. So in our sketch, we are going to make the first quadrant pronounced. Okay, so our sketch is going to be dominated by the first quadrant. So if this is 0, 10, then we have 310, a local maximum at 310. So let's put 310 here. And at 310, the graph is taking this shape. Okay, so at 310, the graph is shaped like this. Okay, then the other point we know is 1, 6. Okay, so 1, 6 is going to be to the left of this point and much below. So suppose we take this to be 1, 6. At this point, the graph has got this shape because we have got a local minimum there. Now, this is now suggestive of what the general shape of this graph should look like, because it passes through this point. So this suggests that it comes down through this point and then up through that point and then back down again. There are no other stationary points. That means like this way it can't turn again, because if that is possible, we could have found that point. So what we do is we just join these points as suggested by these shapes, and then we have the shape of our graph. Okay, so our graph is generally going to look like that. Let's try to make it as smooth as we can. So generally our graph is going to look something like this. I think we can do a bit better. So again, here we go. And then up. And then, so this is 310. This is 1, 6. This is 0, 10. So that is the shape of our graph. Now, from this graph, it suggests that there is going to be an inflection point. It suggests that there's going to be an inflection point in this neighborhood here, because this side is concave up, this side is concave down. So, but let's use the calculus to sort that out. So in part 3, we're looking for the inflection point. The inflection point we find by taking the second order derivative and equating it to 0. So in this case, the second order derivative, which we found here, is 12 minus 6x. So if we take that and equate it to 0, then we find that x is equal to 2. Then for the y coordinate, if we take this and plug it into the y equation, 6 times 2 squared here minus 2 cubed, we find that y is 8. So this is telling us that 2, 8 is an inflection point, and there is only one inflection point here, because this is only giving us one solution. So 2, 8 is going to be our inflection point. Then in the next section, we are looking for the points where the graph is concave up and where the graph is concave down. Those are going to be separated by the inflection point. So the fact that there's only one inflection point means that there are two separate regions of concavity. Okay, so on the left hand side of 2, the graph is concave up. So we're going to say concave up over the interval x is between infinity, negative infinity, and 2. And then the graph is going to be concave down over. So the section of the graph on the right hand side of 2 is concave down. Just something to note about the inflection point for cubics. This only applies for cubics. These coordinates are going to be the average of these coordinates. For instance, if you take 3 and 1 and do the average, this is 4 over 2, this is 2, which is this value there. If you take 10 and 6, 10 plus 6 over 2, this is 16 over 2. This is 8, which is the y coordinate. This is always going to be the case for cubics, but it only applies for cubics. So you can always use that to confirm that the coordinates of your inflection point are correct with respect to the two relative or local extremum points. So, and then the last thing we are required to do here is to find the intervals of increase and decrease. And those ones are separated by the stationary points. Since we've got two stationary points here, there are going to be three regions of increase and decrease. Here the graph is decreasing, there the graph is decreasing. So the left hand side of 1, so we're going to say decreasing over. On the left hand side of 1, the graph is decreasing. Then we're going to say union. On the right hand side of 3 as well, the graph is decreasing. And then it's only increasing between 1 and 3. So we're going to say increasing over the interval between 1 and 3. Between 1 and 3. And that completes the first question. Okay. At this point, we are going to give you an opportunity to have a go at part B. So if you want to have a go at part B, you can pause the video, and then when you continue, you press play, then you're going to find our solution. Then C and D we're going to do in the next video. Okay, we're now going to scroll down to our solution for B. So in B we've got x cubed minus 12x plus 7. First order derivative is going to be 3x squared minus 12. Second order derivative is 6x. And so again, for the stationary points, we take the first order derivative and equate it to 0. 3 is common here, so this thing gives us x squared minus 4 is 0. Solving gives us plus or minus 2. So again, there are two stationary points. So if we go into the x equals to 2, 1, we find that y is going to be negative 9. So 2, negative 9 is a stationary point. If we plug in 2 into the second order derivative, then we find that the second order derivative is positive, which means the graph is concave up. So we've got a local minimum or relative minimum at 2, -9. Then if we do the same thing for x is -2, find that y is 23. So the point is -2, 23. If we plug this in the second order derivative, it gives us a negative, so it's concave down. So -223 is a local maximum. The other thing, which is a logical thing that you can always use to check your calculations here, is that if there are two stationary points, then the minimum should always be lower than the maximum. You can't have the maximum being lower than the minimum if they are the only two stationary points. Okay, so here 23 is much higher than -9, so that makes sense. The y-intercept is 0, 7. So with these 3 points, we can now make a sketch of the graph. -223 is in the second quadrant, so somewhere here. The graph looks something like this. Okay, so that's from there. And then 2, -9 is in the fourth quadrant. So somewhere there, the graph looks like that. And then it goes through 0, 7. Okay, so these three suggest that the graph must look something like that in general. Okay, this is 2, -9. This is 0, 7. This is -2, 23. Okay, and then from here, this is suggesting that we must have only one point of inflection, because the graph is concave up one side and concave down the other side. So there must be an inflection point somewhere in between the two local extreme points. So let's go on with that. So the inflection point we're going to find by equating this to 0. So this gives us x equals to 0. So we already have this, so that means the inflection point actually coincides with the y-intercept. Using what we mentioned earlier, if you take the average of these, then you get this point, so that means that is okay. Then the graph is going to be concave, down on the left of the inflection point. So concave down over, let's just say x is less than 0. And then concave up over x is greater than 0. And then lastly, the graph is increasing on the left of 2, -2, and on the right of 2. So increasing over, so on the left of -2, that's x is less than -2, or x is greater than 2. This is union here. And then the graph is decreasing between -2 and 2. So between -2 and 2, the graph is decreasing. And that finishes up the analysis of this. Thank you for watching. In the next video, we are going to continue with these other two cubics. Where are we? Yes, we're going to continue with these other two cubics. Yeah, so thank you for watching. Hopefully it's been useful. Please do subscribe, of course, and share with friends the link for this channel and like the video. Thank you.